All right, hey, today we're talking about energies and reactions, which is going to be our focus for the next little bit. So this is a bit of an introduction. So what you have here happening is a chemical reaction. It's happening right now. It also looks like it's been happening for quite a while. In this one, if it comes up, there we go, we also have a chemical reaction happening. Not right now, but a few years ago. And the thing about this one is that if you were close to this reaction compared to the previous reaction, that'd be a bit of a concern. So both of them are chemical reactions, but they're also kind of different. And one of the things that's different about them is how fast they are reacting. Yes, it is different things reacting, but the other thing that's happening is that one is happening very slowly, the other is happening much more quickly. And we're going to define reaction rate as how fast reactants convert to products, and we're going to measure it in different ways. We're going to express it in a couple of different ways as well. The other thing that was different about those two reactions is the amount of energy that was released. I'm going to go back to that for a second. Now, you could argue that the first one could have been releasing a lot of energy, but because it's happening so slowly, it was hard to tell, and you'd actually be right. But when we talk about energy being released, that generates a few questions. One of them is, what about the law of conservation of energy? Because that states, as you know, that energy cannot be created or destroyed. So if it's releasing energy, that energy had to come from somewhere, and that's going to be one of the things we have to deal with. And then the other thing is, about that is, does every chemical reaction involve an energy change? For example, going back to that rusting car, does it have energy change going on as well? And then the third question that I think is going to need to be answered, and we're going to answer it very, very soon, is, are there reactions where energy is absorbed, taken in? And the answer is yes, but they're a little bit less common in terms of reactions that you would be familiar with. So if we take try and represent as a diagram where we have a chemical reaction represented as a system, and we're going to make that a circle, and then we're going to put the surroundings, which is everything that is not the chemical reaction, we're going to put that in a box. And then we don't really need to divide it, other than sometimes energy comes out of that system and goes into the surroundings. And we're going to call that exothermic, and that's a term that's going to be important to know. So if you haven't been getting other things down, get that down. Exothermic reactions, energy's coming out. And then you're going to have reactions where energy goes in, and that's going to be called endothermic. Now, there are other terms, so if you've seen them in a different course and you've seen other terms, they're possible. These are the terms that we are going to be using. We are also going to be talking about something called the enthalpy change, which is delta H. Sometimes called the heat change, but because heat and heat energy end up becoming a little bit of a confusing topic once you really get into it, I'm going to try and stick with the term enthalpy as much as I can. But enthalpy is the total amount of energy. The problem is total amount of energy is really hard, in other words, impossible to define and to measure. Well, I guess it's easy to define, but it's impossible to measure. So we're going to talk about the enthalpy change. So if everything else stays the same, then the change in energy is the enthalpy change. That is going to be our focus. And it's always the energy of the products minus the reactants. And what you end up with is, if energy of the products, the energy contained in the products, is less or more than the energy in the reactants, that's going to affect the algebraic sign of our overall calculation. So, and then, change my thought here. And then we're also going to be talking about that in terms of molar amounts, because if you have a small amount of reactant versus a large amount of reactant, it's going to be a different amount of energy. Okay, so when we talk about energy changes and reactions, I already mentioned exothermic and endothermic. Here's a little bit better definition for an exothermic reaction. So the energy of the products is lower than the energy of the reactants. That means small number minus big number. Okay. Energy is going to be released into the surroundings. So what does that mean in terms of what you would experience? Because you will be part of the surroundings. So if energy is coming out into the surroundings, what would you feel? Well, you would feel the thing being warm. The container is going to be part of the surroundings as well. The other side of that was an endothermic reaction, where the chemical energy of this system increases. Now, I know earlier I said that heat energy gets absorbed, but we need to be careful about that, because it's not going to be absorbed and preserved, not going to be absorbed and stored as heat. It's going to be converted into chemical energy. So the chemical energy increases. Again, if it's coming out of the surroundings, if the heat energy comes out of the surroundings and goes into the system, what you would notice as being part of the surroundings is the temperature would go down. It would start to feel cold because heat energy is coming out of you as part of the surroundings and going into the system but converted into chemical energy. Okay, we need to be able to represent that. It's not enough just to talk about it qualitatively, we need to talk about it in quantitative terms. And that brings us to thermochemical reaction equations, which sounds like it's crazy because it is. And we've got different ways of expressing it. So we have to then express these things in ways that are convenient. And sometimes convenient is not convenient, and other times something else is convenient. So we're going to use, those 4 ways of expressing heat change or enthalpy change in a chemical reaction. Okay, so starting out with thermochemical equations, where basically we just write a chemical equation as we used to always do, but then put a heat term there. And by the way, where it says XO in brackets, that is never written in the reaction equation. It's just that's what an exothermic reaction looks like. Reactants turned to products plus energy. An example would be combustion of, in this case, methane, where you produce a certain amount of heat energy. If you had an endothermic reaction, it would be reactants plus energy turn into products. And again, you would not write the endo in brackets ever. It's just that's an example of an endothermic reaction. To do an actual chemical reaction where that's happening, it would look something like this, where the heat energy is on the reactant side. Please don't say that heat energy is a reactant, because it's not. A reactant is a chemical, not an energy. Okay, we can also write them with enthalpy terms written as a delta H value. So in an exothermic reaction, it would look like that. Exactly the same reaction, exactly the same amount of heat energy, but 2 things are different. 1, we've taken the heat energy term out and stuck it over on the side. And 2, in an exothermic reaction, the enthalpy change is negative because the products have less energy. And in an endothermic reaction, we've added energy to the system, so it's a positive value. That's important to know as well. The numbers, not so much. The algebraic signs for enthalpy change, yes. We can also do diagrams. Now, diagrams are not really going to be that helpful to us for a while, but we talk about the potential energy because that's what's changing over time as the reaction proceeds. Well, we start out with reactants and they become products. And there's an energy change associated with that, chemical change. And that energy change is the enthalpy change. So that's an exothermic reaction as a diagram. Now, this isn't scale, and that's where we run into a difficulty. For an endothermic reaction, it would be very similar, except of course energy has gone in. I said energy. Energy has gone into the system, so it goes up. One time somebody asked me, why don't I ever edit these things? I don't. You can also write them as enthalpy terms, and there's a couple of different ways of doing that. Tables I meant. See, I'm not going to edit that. Tables. Now you will find enthalpy tables. You can find one that says molar enthalpy combustion, and it has all kinds of different chemicals in there that can undergo combustion. So you were going to say combustion, and that immediately tells us what is going on, what kind of reaction it is, and what the reaction looks like. And then you just write the value. And because we know what propane is, not yet, and because we know what propanol is, maybe not yet, all we need to know is the number. Too easy. And you can also have one for vaporization, where instead of combusting something, you are evaporating it, turning it from a liquid into a gas, and you can have the numbers for that. So those 2, by the way, the last 2, are not a chemical change, they're a physical change, which you knew that. But you can do enthalpy changes for a physical change as well. Okay, what if you don't have a table? Well, sometimes what we'll do is we will write the delta H and then have some kind of notation to say what kind of process we're talking about. So not this kind, combustion of propane, we identify the chemical. Maybe we use a chemical formula, maybe we use the words, and then we write the name. We write the number. And that tells us everything we need to know. Or for vaporization, you could have the same kind of thing. Delta H of vaporization, you could write out the whole thing. I didn't. I used the chemical formula because ethylene glycol looked like a lot of writing. All those sort of subscripts, and the number for that. Except, don't write that number down because that number is wrong. It is not a negative number. It should actually be a positive number because I'm vaporizing. I'm adding energy to evaporate it. Not only do I not edit my presentation, I don't edit that presentation. Okay, a couple of other things to keep in mind. Number one, it is proportional to the amounts. More stuff, more energy. So if you had the combustion of methane and you doubled everything, you would absolutely double the amount of energy. There's where the negative 889 comes from. Weird. You can also, that was the only other thing, I guess. So that brings us to where I wrap this up. And those are the things we've talked about today. We're going to practice that in class, and then we're going to move on from there. We're going to get into more the quantifiable or the quantity things you have to do with those numbers pretty soon. Talk to you in class. Hopefully I've got myself sorted out by then.